Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 6.3, Sampling Distributions and Estimators. We're going to start off this lecture talking about a rolling dice experiment, which will lead us into a discussion on sampling distributions. We'll talk about bias and estimators, and note some observations on sampling, and then round up the lecture with some look at how to construct sampling distribution tables. So, key concepts for this particular section. First, the individual statistics that we've been looking at, such as mean, standard deviation, so on and so forth, they have sampling distributions. A sampling distribution of a statistic is simply the distribution of all values of that statistic when all possible samples of the same size are taken from the same population. So you're taking samples of the same size from a population, and you're looking at sample statistics for each of those samples that you take out of the population, and putting those values together into its own distribution. We can do this for the mean, for the variance, for the standard deviation, and quite frankly any other sample statistic that we can calculate. What we're going to observe is that some statistics are better at predicting and estimating population parameters than others. So let's get into that. To do that, we're going to have a little bit of an experiment here with rolling dice. So we're going to use the outcomes of dice rolls to make our own distribution, to illustrate how sampling distributions work. What we want to do is characterize the entire population, but in order to get the entire population of rolling dice, we'd be sitting around forever rolling the dice. We don't want to do that. So what we need is another way in which we can take samples from the population and then use the statistics from that sample to estimate the parameters for the entire population. But we need to sample the population in such a way that our samples are characteristic of the larger population. So let's use an experiment where we're rolling dice to see how this can actually work. So the population for dice rolls would be every roll that we could possibly make. Here our sample space contains an infinite number of outcomes. As I said before, if we wanted to get the population of dice rolls, we'd be sitting around forever rolling dice. And I'm guessing most of us aren't going to want to be doing that. However, a sample of dice rolls would be every roll that we actually make. This is a sample space that contains a finite number of outcomes. And this is much more manageable because we can control the number of times that we're rolling the dice, and we can see how many times that we actually need to roll it in order to get sample statistics that are good predictors of the population parameters. So let's design our experiment here. First question we have to answer is, how many dice rolls must we make in order to have a large enough sample size that resembles, so that we have the characteristics to resemble the population? Well, first of all, what do we expect the mean value of our dice rolls to be? Well, the mean value is the expected value, which we learned previously is the sum of the product of each of the random variables and their associated probabilities. So let's go ahead and make a table and calculate this out. So the possible rolls of the dice that we could have, 1, 2, 3, 4, 5, and 6 for your standard six-sided die. These are the possible outcomes for your standard six-sided die. The probability of getting a 1 as the outcome for our roll is 1 out of 6. It's one outcome out of 6 total possibilities, so 1 over 6. We have the same probability of rolling a 2, or in fact any other number on the die. So the probability of getting any one number on the die is 1 out of 6. So now in order to calculate the expected value, we multiply each of these random variables by their associated probabilities. So 1 times 1/6 gives us 1/6. 2 times 1/6 gives us 2/6, and so on and so forth for the rest of the values in the table. Now, to get the expected value, we add these products together. That's the formula for expected value. So we take 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6, we get 21/6, which when you divide out gives you 3.5. So the expected value, 3.5, is what we would anticipate the population mean to be. Now, let's roll the dice 5 times, or excuse me, let's roll 5 dice at a time, because this will allow us to get the samples that we need to form our sampling distribution. Every time we roll the 5 dice, we're going to get a separate outcome for each individual die, and then we can take those numbers and calculate whatever sample statistic we want, whether it's the mean, variance, standard deviation, what have you. So let's roll 5 dice at a time. This allows us to calculate, as I said, sample means after rolling 5 dice, and we'll calculate a new sample mean after each roll. So the first roll of the 5 dice will be one sample, the second roll of the 5 dice will be a second sample, so on and so forth. And for each of those samples, we can calculate a separate mean value and whatever other statistic we want. As our sample size becomes large enough to resemble the population, the sample mean should approach or target the population mean. And then the population mean is the expected value that we just calculated, the 3.5. So let's see how well the sample mean targets the population mean. So let's roll the dice for the first time, and when we do that, here's the results that we get. We roll a 3, a 2, a 1, a 2, and a 2. So let's make a table where we're actually calculating out our sample statistics. So the first trial, we roll the 5 dice. We have a mean value of 2. If we take 3 plus 2 plus 1 plus 2 plus 2, then divide by 5, we get 2. Our sample size is 5. The sample mean is 2. So now we're going to roll the dice a second time, and we get these results: a 1, a 6, a 4, a 3, and a 1. So for the second trial, the mean value of these numbers is 3. But when we add it together with the 5 dice that we rolled the first time, our sample size is now 10. And if we take the mean value of all the numbers that we have, the sample mean is now 2.5. Rolling the dice a third time gives us these results, which, when we add our values to the table, we find that for this third trial, the mean value is 4.2. When we add these 5 new values to the 10 we have already, now we have 15 total, and the sample of all 15 of these numbers is 3.07. We roll the dice a fourth time, and we get these results out: a 6, a 4, a 3, a 6, and a 4. So now, for this fourth trial, the mean value is 4.6, but if we take the sample size of 20, which is all 20 numbers that we've collected so far, the sample mean is now 3.45. So it looks like the values for the sample mean are approaching our expected value of 3.5. Let's roll the dice 20 times so that we have 100 outcomes in our sample. When we do that, we get the values that you see here in the table below. The sample mean is 3.44, sample variance 2.73, and sample standard deviation of 1.65. At this point, we want to take advantage of living in the 21st century and use simulations. This way, we don't have to actually perform the actual rolls. The computer does it for us. And the reason why we use computers is because they're great for counting and collecting data. That's what they were made to do. So let's go ahead and use it for that purpose. The other reason why we want to perform a simulation is because we'll get results much faster than we actually will performing it ourselves. You set up a simulation, you hit the go button, and in a matter of a fraction of a second, you've got all the outcomes from your simulation, which mirror what you would get if you were actually doing the actual procedure in the real world. So simulations are definitely the way to go when you have a lot of outcomes you want to produce. The StatCrunch has a feature where it can perform simulations of simple experiments like rolling dice. So this is what I'll actually use to conduct our simulation for dice rolls. So we have, as I showed you in the table, when we do this for 100, sample size of 100, sample mean of 3.44, and the other statistics you see there. But what do we get if we keep rolling? Let's say we want a sample size of 1,000 or 10,000. What will the values be then? Well, let's find out. If you actually run the simulation, this is what you get. So notice here on the chart, you've got along your horizontal axis the number of runs that you're conducting. So here at 2,000 runs, we're sitting right about here with the proportion of, let's see, average number of rolls is of 1 rolls is less or greater than or equal to 3.5. So yeah, this is the proportion for the outcomes where you're looking at the proportion. So it's like, so how many times were we actually rolling the dice, one die with 6 sides, and we're actually going to roll the dice and then get our outcomes out. And notice how we have some outcomes that are above the expected value of 3.5 and below the value of 3.5. And this is the proportion that we're actually calculating here. So for a 6-sided die with an equal probability of getting any one of the 6 numbers, you would expect half the outcomes to be below 3.5 and half the outcomes to be above 3.5. And that's pretty much what we see here, that as we roll the dice, it quickly comes up to about this halfway point of 50%, and then it bobs itself up and down, but then it eventually gets to the point where it levels out at about 0.5. Notice that after 10,000 trials, the proportion of runs that are on one side or the other is actually slightly less than 50%, but it's close enough to where we would actually consider it to be about a half. Notice how the sample mean, the variance, and the standard deviation are changing the more time we actually take the rolls. So here we go from 3.44 with 100 rolls for the sample mean, up to, for 1,000 rolls, we've got 3.5. So now we've hit our expected value, but the more times you roll it, look, if we go another order of magnitude up to 10,000 rolls, we dip slightly down to 3.49. As you see in the graph here, the farther out you get along your horizontal axis, the more what's the best way to say this? The line here is still bobbing up and down above and below 3.5, but the amplitude of your oscillations is getting smaller as the further out you go. So it's actually bobbing less the further out you go, but it's still bobbing a little bit. Notice about half of these 10,000 outcomes, as I said before, are above the mean, which is the 3.5, and then half of them are below the mean. This is what we would expect. Notice also that this condition of it leveling out at about the halfway mark occurs around 1,000 rolls. So really, we don't need to roll the dice more than 1,000 rolls in order to find a sample mean value that estimates very well the population mean value. If we make a histogram of the individual outcomes in our sample space, what we end up with is uniform distribution. This is to be expected because we have an equal probability of getting any one of the 6 outcomes. So here's the 3 outcomes that are above the mean value of 3.5. Here's the 3 outcome values that are below 3.5. And what we see here are the frequencies of their occurrence within the sample distribution. Notice how it's more or less the same. Not exactly, but more or less the same. And this is what we would expect since we have an equal likelihood of getting any one of these 6 outcomes. If we make a histogram of the mean values in groups of 5 outcomes to represent rolling 5 dice at a time, what we get is a normal distribution. So the mean values are normally distributed about a mean value, which is the expected value. Notice how we have that bell shape to our distribution, and notice that the center of the distribution is right around 3.5, which is the expected value for the population of dice rolls. Notice also the proportion in each case targets 50%, as we would expect. We'd also get a normal distribution with a histogram of the proportions of each group of 5 outcomes that are above and below the population mean. So if we looked at samples for the mean value, so the mean value for each of the 5 dice rolls that we make, we take those mean values and we organize them into a distribution, and we would see that half of them are above the mean value and half of them are below. So we're getting a normal distribution whether we're looking at proportions or we're looking at means. The sampling distribution of the sample mean is therefore the distribution of all possible sample means, with all samples having the same sample size n taken from the same population. So for every sample of 5 dice rolls that we take from the population, we can put those values together to form a distribution, and that distribution will conform to the normal distribution. In our dice rolling experiment, we have a sample size of 5, because we're rolling dice 5 at a time. So each of these samples are taken from the same population. As we see, sample means target the value of the population mean. The mean for our distribution is 3.5, which is the expected value for the entire population of dice rolls. So the mean of the sample means is the population mean. The expected value of the sample mean is therefore equal to the population mean. The distribution of the sample means also tends to be a normal distribution. So all the tools that we've learned about so far here in Chapter 6, we can use when taking samples from a population and then calculating the mean values for each of those samples. Because we saw the same features with sample proportions as with sample means, then we're going to have the same characteristics for the sampling distribution of sample proportions. So its distribution will also be normal, and the population proportion will be targeted by the sample proportions. Well, that's all fine and dandy for means and proportions, but what about sample variances and standard deviations? Well, if we make a histogram for the variance values of groups of 5 outcomes at a time, what we get is something that looks like this, which is a skewed distribution. Notice it's not centered around itself. It doesn't have that characteristic bell shape, and there's certainly more data on one side of the graph than there is on the other. So remember, statisticians, when they're talking about skewness, they look for the larger tail when describing a skewed distribution. So we would say that this distribution is skewed to the right. However, my friends in industry would look at this and say, well, the data is skewed to the left, because that's where the bulk of the data is residing, towards the left side of the graph. But that's not how the author of your textbook would describe it. He would describe it as being skewed to the right. So the variance for infinite outcomes is going to be 2.9. So our sample size of 10,000 trials is best to target that population variance. So notice how we have to have more trials. We have to have a larger sample size in order to target better the sample variance. Notice, however, that we have 50% of the outcomes are below the mean value for the distribution, and 50% are above the mean value for this distribution, as we would expect it to be. So the sampling distribution of the sample variance is the distribution of all sample variances with all samples having the same sample size n from the same population. So again, our sample size is 5 because we're rolling dice 5 at a time, and all samples are taken from the same population. Sample variances will target the population variance. So the mean of the sample variances will be the population variance. Again, we're taking the mean because the mean is a good target of a sample statistic for a population parameter. The expected value of the sample variance is equal to the to the population variance. And the distribution of the sample variances tends to be skewed to the right, as viewed by a statistician. This leads us to the concept of bias in estimators. Some sample statistics are what we call unbiased estimators because they target well their respective population parameter. So we have the mean, the variance, and proportion. These sample statistics target well their respective population parameters. So taking the mean of the mean values, or the mean of the variances, or the mean of the proportions for the samples that we take from a larger population, these values are going to target well their respective population parameters. Note there's a nomenclature that's special for proportions. So typically the population parameter is symbolized with a capital letter, and the sample statistic is characterized with a lowercase letter. Well, here we're dealing with proportions. We're already using a capital letter P to represent probability. So in order to avoid confusion between probability and proportions, we're just going to say, okay, we've already taken the capital letter P and used it for probability. So now we're going to take a lowercase letter p and use it to represent the population proportion. And then we're going to take a little caret sign and put it over the p. And we're going to have this symbol represent the sample proportion. This symbol red is pronounced p hat because the caret symbol over the p looks like a little hat. So therefore we call this p hat. Now, other sample statistics are what we call bias estimators because they do not target well their respective population parameters. These include the median, the range, and the standard deviation. These sample statistics do not target well their respective population parameters. Note that we can use, however, the sample standard deviation to estimate the population standard deviation if we have a sufficiently large sample size. We'll get to that a little bit later in the chapter, but for right now, all you really need to focus on is that, generally speaking, these sample statistics do not target well their respective population parameters, but we can make an adjustment to the sample standard deviation so that it does target well estimate well the population standard deviation. Let's take a look at estimators that are unbiased. So for each of the following sample statistics, identify whether we have an unbiased estimator of a population parameter. So the first example we have is sample mean used to estimate a population mean. Does this sample statistic target well its population parameter? Is it an unbiased estimator? The answer is yes. Sample means are unbiased estimators. They target well the population parameter of the population mean? How about a sample standard deviation used to estimate a population standard deviation? Is this an unbiased estimator? Well, from what we just learned, no, standard deviations are not unbiased estimators. They are biased estimators. There is an adjustment that we can make, but without that adjustment, the standard deviation is going to be a biased estimator of the population parameter. How about the sample range used to estimate a population range? This is also an example of a biased estimator. So, sample range, we can't use that to estimate the population range because it's biased. It tends not to target well that population parameter. Sample median, used to estimate a population median. Yes, once more, we have another example of a biased estimator. So the sample median is not going to target well the population median. How about a sample proportion used to estimate a population proportion? This is an example where, yes, if we take the means of the sample proportions, we can use that to estimate the population proportion. How about a sample variance? Can the sample variance be used to estimate a population variance? And the answer is yes. We take the mean values of the sample variances for the samples we take from the larger population. We can use that to estimate a population variance. Let's make some observations on sampling. So what we've learned so far in statistics is that there are many methods that require a simple random sample. Some sample types, such as voluntary response or convenience sampling, could very easily yield very wrong results because these sampling methods typically do not produce samples that are characteristic of the larger populations from which they are taken. The question comes up, though, is that even if we have a sampling method that's going to give us a simple random sample, should we sample with or without replacement? That's an excellent question. Well, in the first place, sampling without replacement will avoid a lot of wasteful duplication whenever the same item is selected more than once. And for most real-world applications, this is what we want. We want to sample with replacement. Why would we sample with replacement? Well, in the first place, when we're selecting a relatively small sample from a large population, it really doesn't make any much difference whether we sample with replacement or without replacement, because the sample size is so small relative to the size of the entire population. However, sampling with replacement will result in independent events that are unaffected by previous outcomes. And as we've seen previously, independent events are easier to analyze and they result in simpler calculations and formulas. So, yes, we go ahead and sample with replacement for most real-world applications. This brings us to creating what's called a sampling distribution. So for the remainder of this lecture, I'm going to go over a typical type of problem that we see with sampling distributions, and that is creating what's called a sampling distribution table. For this particular example, let's assume we have a population of the numbers 2, 4, and 8, and that sample sizes of 2 are randomly selected with replacement from this population. So we have the numbers 2, 4, and 8, and we're going to randomly select 2 of those 3 numbers, and then put those numbers back in to be selected potentially again. First, we're asked to find the value of the population standard deviation. Then we're asked to find the standard deviation for each of the 9 samples, summarizing the sample distribution of the standard deviations in the format of a table, representing the probability distribution of the distinct standard deviation values. Use ascending order of the sample standard deviations. 3. Find the mean of the sampling distribution of the sample standard deviations. And 4. Do the sample standard deviations target the value of the population standard deviation? In general, do sample standard deviations make good estimators of population standard deviations, and why or why not? So what we're going to run through is a typical type of problem, and you can use any type of sample statistic to go through this process. It's the same process, but for an example, for purposes of this lecture, I've selected to use standard deviation, but you could easily replace standard deviation with the mean or whatever other sample statistic you want to evaluate. Now, you can solve these types of problems and make a sampling distribution table in either StatCrunch or Excel. Because I'm a little bit more proficient with Excel and very comfortable with Excel, I find it easier to solve these types of problems in Excel. However, it could be equally easy for you, perhaps, to solve this in StatCrunch. So I'm going to show you how to do it using both platforms, and then let you decide which way do you want to go to solve these types of problems. So let's tackle each question one at a time. And first I'm going to show you how to do this in Excel, since I find it easier to do it in Excel, and then I'll back up and show you how to do the same thing in StatCrunch. So the first question asks us to find the value of the population standard deviation. This question is asking you to find the standard deviation using the individual values in your population. So in Excel, what we're going to use is a special function called stdev.p. This .p on the end of our standard deviation function will calculate the standard deviation for the population, which has a slightly different formula than the standard deviation for a sample. So if we don't put the .p on the end of our function, then Excel is just going to assume that we want a sample standard deviation. And what we end up with is a very different value. So we want to make sure that we go ahead and use the right function with the .p on the end for the population standard deviation. So here's an example of samples that were taken from our population. Remember, we have 3 numbers to choose from, and they're selected with replacement. So we take one number, record it, put it back in. We take another number, record it, put it back in, and those 2 trials then become one sample. So the first time we drew the number 2 twice, and then the second trial we drew the number 2 and then the number 4, and then the third trial we went with a number 2 and then we drew a number 8, and so on and so forth, and we can see all the trials that we have here. The population standard deviation is then going to be, as you can see here from our function, we have standard deviation .p, and then inside the parenthesis we're going to put the actual values from our population, 2, 4, and 8. So there are no cells to select per se. We're actually just going to put the values for our population here in our formula in Excel. Now we could very well select cells to do that, and if we had these values in cells, we could select the cells just as we could for any other function. But there's only 3 values, and so there's no point in making a separate row or column to calculate this out. So that's the way you do it in Excel. Just basically type that function there into one of the cells, hit the enter key, and boom, you've got it. Now you can do the same thing in StatCrunch, but you end up having to put your values in a separate column and then perform column statistics by selecting the unadjusted standard deviation from your list. Let's take a look at how that's done. So we have to add this additional step when we're doing the same sort of problem in StatCrunch. The first thing we need to do is put our values into a separate column, since StatCrunch can't take part of a column or row to calculate values. So here we have the same data that we saw there in Excel, but we actually have to take those values out and put them into a separate column, because unlike Excel, StatCrunch doesn't allow you to put in actual values inside a formula. You have to actually have the values that go into a calculation in a cell itself in the data table. So the only way to do this in StatCrunch is to put in this extra step of making a separate column with the actual values in that column. Once we have that done, we go to Stat, Summary Stats, Columns, and we select the new column in which we put in the values for our population. Now, make sure that when you're in the options window, you go in here and you select your data, and then you're going to scroll down to almost the bottom of the list and select Unadjusted Standard Deviation. Unadjusted is stat speak for population. So, because we want the population standard deviation, notice that's what was asked for in the problem statement, population standard deviation, we need to use this separate function down here towards the bottom of the list in order to get the right value out. Press compute, and then out comes this little results window with the appropriate value. Notice how we get the same number that we got with Excel. But I think Excel is a little bit easier to use simply because I don't have to go through all these extra steps of setting up an extra column and then running through this interface of the options window before I finally get my final result. I simply type in the function, hit enter, and boom, I'm there. Let's look at the next question we were asked. Find the standard deviation of each of the 9 samples, then summarize a sampling distribution of the standard deviations in a probability distribution table. So what this question is asking you to do is find the standard deviation for each individual sample and then assemble those standard deviations into a distribution table. In Excel, you can calculate a separate standard deviation for each of the rows in your data table very easily. So going back to our data table, notice I have here out to the side standard deviation for these 2 cells marked here. So for the first sample of 2 trials, I've got a standard deviation of 0. Then I copy that formula down so it calculates it automatically for each of the 9 samples. Now I have individual standard deviations for each of my 9 samples. To get to where I want to be, though, I have to take the mean value of each of these standard deviations. Now notice what we're using here. Because we're calculating sample standard deviations, I don't have the dot p here on my function. So I want sample standard deviations when I'm calculating each individual sample, but for the population, I want to get the dot p in because that gives me the population standard deviation. It's a different calculation, so you have to remember to keep those separate. This is part of the reason why sample standard deviations by themselves are not good estimates of population standard deviations. But we'll see that here as we finish out the problem. Now we can construct our table with the values that we have here, but I find it easier to sort the values first. So here on the next slide, I'll show you how that's done. What I do is I take these values and I copy and paste only the values into the next column. Because remember, these cells here in column D actually contain formulas. I don't want to copy the formulas over, just the individual values. So I'm going to go paste special and then paste in only the values from that column here just right next to it. Then I'm going to select that next column and select Sort, which is found in the Data menu ribbon. Now Excel, when you do this, because you've got data sitting right next to the data that you've selected, Excel is going to automatically ask you Do you want to expand your selection to include the neighboring cells? You don't want to do this. You just want to sort the one column, not all of the columns together. So go ahead and select just the one column. Continue with your current selection. The default will organize the values from smallest to largest. This is what we want, so there's no need to change anything. Just when Excel asks you to expand the selection, just say you just want to continue on with what you're doing. You don't want to make any adjustments. Go ahead and click OK, and then when you do that, you get sorted values here from which you can create a probability table of random variables and their associated probabilities. And now with the data sorted, creating this table is super easy. Let me show you how this is done. We want to place the lowest value in our column in the first position. Because we sorted the data, that value is very easy to spot. It's right here at the top. So we're going to put 0 in as our first random variable because it's the lowest value here in the column. Its probability is going to be 3 over 9. Why 3 over 9? Well, because we have 3 zeros and there's 9 numbers total. So 3 out of 9. 3 is the part, 9 is the whole, so the probability, part over whole, will be 3 over 9, which we can simplify to be 1 over 3. So 1/3 is the value that goes here. The next value in our table will be 1.41. This is the next lowest value, and we place this in the next position for the column of random variables. Its probability is going to be 2 over 9 because we have this number repeated twice. So there's 2 occurrences of this number. There are 9 numbers total, so the part over the whole is 2 over 9, which then gives us our probability. We then run through this for the remaining numbers that are there in our column, and we finish out our probability table. Easy peasy. We can also check to make sure that we've got the right numbers, by just remembering that for a probability distribution, all the probabilities have to add together to be 1. So we add 1/3, 2/9, 2/9, and 2/9 together, and indeed we do get exactly 1 coming out of that. So this checks out. We can do the same thing in StatCrunch, but the way you have to go through it, it's a little bit more clunky. Still, if you prefer to use StatCrunch, this may be your approach of choice. So the first step you want to do is go to Stat, Summary Stats, and then Rows. Notice we usually select columns when going to Summary Stats, but for this particular application, you're going to want to select Rows. Then you're going to select the columns that contain the data of your statistic. So in this example, we just want the X1 and the X2 because that's where the trial outcomes for our samples are located. We're going to calculate a sample standard deviation for each one. Notice we're not doing population, we're doing sample standard deviation. Once we have that selected, we're going to press compute, and out comes this wonderful little results table. This is equivalent to the column D that we saw earlier in the example for Excel. Sorting this data is a little bit easier in StatCrunch than it is in Excel, because all I have to do is take this little arrow, this little double arrow right here at the top of my standard deviation column, and I press that with my mouse. Left click it with your mouse, and automatically everything's already organized for you. Now, if you hit that button again, it'll reverse the order, sorting it from largest to smallest, and you can toggle back and forth as you press that little arrow button. But now I have the same sorted column of values that I had before in column E in Excel, and now I can take these values and make the probability distribution table just as I showed you earlier. The next question asks us to find the mean of the sampling distribution of the sample standard deviations. So what we're asked to do is to take each of those sample standard deviations, take those values together, and calculate the mean of those values together. In Excel, we're just going to use the average function to calculate this. So again, here are my values, and it doesn't matter if you choose the unsorted or the sorted column. They're the same numbers, and average will calculate the same way out. So here I've calculated the average of my sample standard deviations, and I get the number that you see here. You can do this in StatCrunch as well, but again, you also need an extra step. So in StatCrunch, you're going to go to your options window. From your results window, select Edit to go back to the options window. And then in the options window, you're going to check the box down here at the bottom that's next to Store in Data Table. When you press Compute, what ends up happening is that your results are now placed in your data table instead of a separate results window. So notice here how instead of a separate results window, the data is placed right here with the rest of the original data that was used to make these calculations. This is important because now that I have these numbers in the data table, I just go back up to Stat, Summary Stat, Columns, and select the mean value for these values here, and here we get the same number that we got in Excel. So it gets you to the same spot, but you have to go through an extra step to get there. The last question we were asked is, do the sample standard deviations target the value of the population standard deviation? In general, do sample standard deviations make good estimators of population standard deviations, and why or why not? So what we're being asked is to compare these two numbers that we calculated down here at the bottom. And this is another reason why I like to do this in Excel, because now I've got both of those numbers sitting side by side together. Whereas with StatCrunch, I've got to remember, okay, the one number was in which window, and then I've got to get the window for the other number, and I've got to put them together so I can actually do the comparison. Whereas in Excel, there is no hunting for these different result windows. I've got both my numbers sitting here side by side. So it makes it a lot easier to make that comparison. So when you go to StatCrunch, you've got to, I guess the other option would be to write it down, as it says here. Just go ahead and write it down so you can compare the numbers. But again, that's an extra step. And so me being the lazy engineer, I want to avoid the lazy step. And this is, pretty much why I'm looking at this in Excel, because I can avoid that extra step. Now, the number of samples in our distribution is small. Okay, so the right answer for these questions, these types of questions, is always going to be that the unbiased estimators target the population parameter and biased ones don't. It doesn't matter how close the numbers are together. You might say that 2.49 is pretty close to 1.88, but you might say that they're not close together. What you want to look at is not how close the numbers are together. When you're answering this question of, in general, does the sample statistic make a good estimator of the population parameter? You're going to look and say, well, what's the statistic in the parameter? In this case, it's standard deviation. And as we learned earlier, standard deviations are biased estimators. Therefore, they do not make good estimators of population standard deviation. And you can see here, there's quite a difference here in our standard deviation values. So it doesn't matter how close the numbers are, though. Even if the numbers were very close, the correct answer is going to be based on whether the estimator is biased or unbiased. So you have to pretty much remember which ones are biased and which ones are not. That brings us to the end of this lecture and this video. If you have any questions, you know what you need to do. Otherwise, I will see you in class or the next video. Thanks for watching.